It's a pleasure to be here. I will try to keep us on time, or maybe even get us back on schedule. We'll see how we do. So yeah, let's just dive right into it, right? So where did we all start with this? We actually started looking at mechanics of 2D materials, or especially mechanics of graphene, because I was interested in making graphene nanomechanical devices. So if we're on time, I'll get back to those toward the end. But we were also making electrical devices where we were trying to eliminate substrate effects. So we heard from Deji about how contamination and substrate effects are dominant for all of the 2D materials. And we were looking at making structures like this. And there were a few other groups that had started doing mechanical testing of graphene in this kind of a configuration, where you push on the middle here, and you see how this ribbon, very wide ribbon, but the suspended membrane deflects. And this is very nice, but it gives you some, it has some problems, right? It has once you indent this, you actually have a complicated stress state, and you also have issues with clamping and edges. So as soon as you have a small defect at the edge, you tear, and you're not seeing the intrinsic properties of the graphene. Right? So what we set out to do, this is now ancient history, so this is our paper from 2008. What we set out to do, and again, when I say we, it was a very good postdoc, Changgu Li, who started doing this on his own without telling me. So I get full credit for the idea. So what he set out to do, let me use the right pronoun, is a slightly different approach, which actually turned out to be much more elegant and eliminate a lot of these problems. So he made circular membranes instead. So he put graphene over circular holes, just exfoliated, and then came in with an AFM tip and did a nanoindentation test in the center of those sheets. Right? So I think maybe I don't need to go through, this is from a previous talk, but all of these holes were made by pretty standard etching. So let me just skip over all of this stuff. See, we saved so many slides already. But that's the idea. We're left with silicon dioxide. There's your circular holes in cross-section, right? And so this is an image of some of these holes. So we have these holes. There's the bottom. Here's the top of the silicon dioxide. And here's a piece of graphene going over the hole. So this is a membrane that's suspended. This is kind of halfway over a hole, and this is an open hole here. So when we do these indentation tests, we get something that looks like this. So this is actually, we don't have a nice system like this. This is our friend Julia Greer at Caltech did this movie. But the idea is we come in with a tip. So this is a diamond tip. I'll talk about in the original experiments. We first started with conventional tips. This is some of these membranes, 1 and 1.5 micron in diameter, looked at from an angle, which is why they look elliptical. And you can see now we're starting to deflect. And there you go. And you can see this graphene is incredibly robust. You can really push the heck out of it. And then we see brittle fracture right at this point. Right? So this is the basic process we want to understand. So here are some of the details of the experiments we did. We did this for a few different graphene flakes, different drumhead diameters. We used different AFM tips, put them right in the center of the film. One thing we noticed, and the reason this experiment took about a year to complete and start writing up, was that we spent a lot of time with regular silicon AFM tips. And if you just kind of don't think about it too much, you think, I've got a material that's 1 atom thick. I've got a somewhat macroscopic tip that's, say, 20 nanometers radius. I should be able to just punch through that no problem, even though the graphene is probably a little stronger than silicon. There's so much more silicon there. Well, it turns out no. So it turns out we kept doing these indentation experiments, and we knew we had to understand the radius of curvature of the tip to see how sharp it is. And so we would look at it in a TEM before and after, and we would always find that the tip was broken after our indentation experiment. And that was actually reflected in kind of, you could see in the force displacement curve, you kind of saw weird bumps and things like that. And we thought it was maybe we were banging the tip into the bottom of the hole at the end of the experiment, but we actually finally managed to see that we could break the tip even without breaking the graphene. Right? So graphene is just that strong. So it took a while to find diamond tips on, again, diamond tips are a relatively standard thing, but diamond tips on relatively flexible, low bending modulus cantilevers are not. That took a long time to find a source of those things. So little experimental details, but in the end we had to use diamond tips. Okay, so we got a lot of data. Here's what this data looked like. So this is one of the first plots from the paper. So we see a force displacement curve. This is in nanonewtons and displacement depth. You can see a curve that looks kind of like this, and you notice that as you start to get to longer, higher displacement, you get this approaches a cubic term, right? So this is on a log-log plot. So you can see this looks like a linear transitioning to a cubic behavior, right? And this actually turns out to be relatively easy to understand. If you think about, I do this when I talk to high school students, you can actually think about the physics of just a string. And if you pull a string, the tension is 2t sine theta. Right? That's we all did that in the first week of a physics class, free body diagrams and vectors. But as you start to stretch the string, right, the string gets longer, and the added length of that string goes like theta squared. It goes like cosine theta. Right? First term is theta squared, which is distance deflection squared. And therefore, the added tension, the tension is not a constant. We have the built-in tension, whatever we pull the string to. And then the additional tension goes like deflection squared. And so in the end, when we do this 2t sine theta, which is 2t times the deflection, we get a linear and a cubic term. Right? So this is nonlinear response from still a linear mechanical response. So we still have F equals kx, or just the linear form of Hooke's law, but because of the geometry, we have a nonlinear geometric response. And so what we can see is that the force in a 2D membrane, you get the analogous thing happening. The force goes like the built-in strain times the first power of the deflection, and then the Young's modulus times the third power of the deflection. Right? So linear plus cubic term, and that's exactly what we see here. So when we fit our data to these models, we got a very nice, we got a lot of scatter because it's very hard to do precise calibration of the force constants and exactly where your laser is on your cantilever and lots of things like that. But with some statistical variation, we get a very nice agreement. We get an effective Young's modulus of about 1 terapascal. Right? Really, the better way to say this, because we have a two-dimensional material, is that the modulus is there's a 2D analog to Young's modulus, and so we say this is units of newtons per meter. So it's about 340 newtons per meter. But if you consider the thickness to be the interlayer separation in graphite, which is what you would have if you scaled this with multiple layers and pulled on it, you get a Young's modulus of 1 terapascal. Right? This is exactly what you see in bulk graphite under tension. We see, of course, that from flake to flake, we have different values of the pre-stress as we expect as well, and I think there's still some not full understanding of where that pre-stress comes from, but we certainly know that the flake does tend to bend over the lip of the hole just a little bit, and the interaction of the graphene with the edge of the hole naturally gives us some pre-stress. So that's certainly going to be sample dependent. Okay, so that was the kind of the first order thing to look at is what is the Young's modulus. But the more interesting thing, of course, is what is the fracture strength of this material. And again, that's why this, if I look, the geometry we have actually turned out to be very interesting. So I actually got into this business a little bit trying to do similar tests on carbon nanotubes, right? So Boris had some very nice predictions for fracture strength of carbon nanotubes as a function of chirality. Years ago, we were growing nanotubes we were kind of characterizing their chirality. I was working with Rod Ruoff to try to pull on these things and break them. And much to Rod's chagrin, we never, we got some data, but we never managed to verify the experimental or the theoretical predictions. And that's because in a one-dimensional carbon nanotube, you always have to clamp, and you always have some stress concentration or some imperfection at the clamp, and they always broke at the clamp. Right? So we got up to about 5% strain, and then we would always break at the clamping point. Right? And that's a kind of a generic problem with a one-dimensional material. If you have a single defect, that's always going to be the weak link, always going to be the weak point. Or the clamp, same thing, because the tension is uniform throughout. On the other hand, if you have a 3D material, you always have a surface which is going to be weaker than the bulk, because the atoms at the surface are only bonded on one side. They have dangling bonds on the other. So you're always going to have some sort of weak point at the surface, and you're always going to have cracks that initiate at the surface and go to the center. In 2D, this turns out to be a sweet spot for doing mechanical testing, because what we could do is clamp at the edge here. So this is a finite element simulation of just the strain or the stress in the material as a function of position as we do this indentation. And what you can see here is that the stress is concentrated just at the area around the tip. Away from the tip, at the edge, the stress is very low, and that means even just the weak van der Waals force of the graphene adhering to the SiO2 surface is enough to hold it in place. And it also means that we're not going to fracture at our clamp, because we have a large area clamp that the load is distributed across a very large area. On the other hand, so all of our fracture mechanics is going to be right at the tip, and at this point we have no free edges. Right? So we get rid of the edge problem. As long as we don't have defects in this center, we should see the intrinsic behavior of graphene rather than extrinsic behavior due to edges and clamping, things like that. All right, so what did we see? So that's kind of going backward. So what we saw is that when we drove these films to failure, we saw that so this is kind of 4 representative plots here. These little X's are the points where the films break. And what we saw is that the fracture force, the fracture load, depended only on the radius of curvature of the tip. Right? So these two curves, one here, are for different size membranes. A smaller diameter gives us a steeper stress-strain response or force displacement response, but it fractures at the same point with the same type of tip. On the other hand, if we use a blunter tip with a larger radius, we need a larger force to fracture. Right? So again, really what that's telling us is, all of the action is here. It's all our fracture is not due to the bulk force displacement response of the membrane. It's all due to the local stress concentration under the tip. So that's very interesting, and we could plot that. So this is the fracture force for the 2 different tips, and you can see we get a nice what looks like to be kind of a Gaussian distribution. Just that distribution actually turns out to be interesting as well. Right? So if you, in kind of normal fracture mechanics, you expect something called a Weibull distribution, and that has with this function here. Right? And the idea behind the Weibull distribution is that if you have random distribution of defects in a material, you're going to get a widely varying statistical variation of breaking strength, and only a few samples will approach kind of the maximum value, and you'll get a long tail below that. So we see more of a Gaussian distribution, which tells us that we're not seeing a statistical distribution of defects or breaking strength. We're seeing something that's intrinsic and really probably with variation due to experimental issues rather than the material itself. Right? So that's kind of this Weibull analysis, as well as just the size of the breaking strength, led us to believe that we were not measuring what you measure in every other material, but we were measuring intrinsic breaking strength due to the breaking of all the bonds at once, rather than propagation of a crack. Okay, so the question is, how do we actually figure out from the breaking force what is the breaking stress? Right? That gives you that tells you actually the strength of the material. Right? And this is, when I talk to high school students or undergrads or anybody about this, this is the lesson I think most of the faculty in the audience will, and many of you have been TAs, you probably hit the same thing, right? The classic thing you see with first year students, especially the pre-med physics classes that we've all enjoyed teaching, the classic approach is, what's the formula for that, right? We all get that, right? And what you try to teach students is that just because there's a formula doesn't mean it's the right formula, even if it has all the right symbols in it, right? And it's, physics is not just match the symbols that you have in the problem to a set of formulas on a formula sheet, plug the values in, right? You're supposed to think about the problem. So in this case, this is a great example of that. You can look up in a book, you can find a formula for that. You can find a formula for the maximum stress on a membrane as a function of force applied and the radius of curvature of the indenter tip. The problem is, this is based on linear mechanics, right? It's based on assuming that the material is in the linear stress strain state. But the problem is, if you look at the magnitude, if you just kind of do a finite element simulation, you look at the magnitude of the strain underneath this tip, it's certainly 10%, 20%. It's incredibly high. And once you see strains like that, you know you're not in the linear regime anymore, right? You have to think about the nonlinear behavior of the material, right? So what we did in this first paper is do the simplest model, right? So of nonlinear stress strain behavior, right? So we said, all right, here's Hooke's law, F equals kx right there. And we just added one more term. We just added a quadratic term. All right? So no problem. We had no idea what this quadratic term was, but this will give us this will be negative. So this gives us an inverted parabola. And from the statistics, if we assume that we're breaking at the intrinsic strength, that means we're breaking at the top of the parabola. Then by changing this value, we can change the stress strain behavior, and we can run a simulation. And so we repeated the simulations for different values of this parameter d. Right? So, and then we could get, for instance, stress as a function of position, and the maximum stress as a function of load. And what you could see is, when you add this nonlinear term, you get a lot less stress at very high loads because you're getting weaker as you start to really stretch those bonds. So what we did was find the maximum stress that, or the maximum force that fit our experimental value, and we got a d of minus 1380 newtons per meter, which gives you a stress strain curve that looks something like this, right? So linear at low strain, as you would expect, every material should do that, and then curving over with an inverse parabola. So the Young's modulus, again, is about 1 terapascal. This was about 2 terapascal, negative 2 terapascals in kind of the bulk equivalent. But the important thing here was that the intrinsic strength, then you just read off from this maximum value here of about 130 gigapascals, which turns into 42 newtons per meter, right? So this is our original value, and this is actually the value that gets most oftenly quoted. It's close, but it's not exactly right, and I'll talk about why it's not exactly right in a couple slides. Just as a kind of a fun diversion, what does this value mean? 100 and something gigapascals for strength. Well, here's the Ashby plot of strength as a function of density for a whole bunch of engineering materials, right? So wood is light but not so strong. You get to ceramics and composites. Graphene is up here. I like showing this because it is literally off the chart. You can actually say that. It's about 100 times stronger than steel. It's a pretty amazing material, both because the carbon-carbon bond is so strong, but also because we're looking at a material at its intrinsic fracture strength rather than fracture due to defects, which is all of these other materials. I think you can see similar results, not quite as high in carbon nanotubes, and things like very ultra small gold wires also show fracture strength much higher than the bulk, as well as small diamond whiskers and glass fibers, things like that. So we tried to think about a kind of an analogy for how strong this material is. The one we came up with is, well, this is, if you imagine that this experiment is like putting a saran wrap over a coffee cup and then trying to poke through it with a pencil. So we said, all right, well, how thick is saran wrap? You look that up and you kind of just scale everything up, give the pencil a radius of about 1 millimeter or so. And we came up with a force of a couple tons it would need to break through that saran wrap. So we said it's kind of like the weight of a small elephant on the pencil. We didn't get any, great prizes for this, but we got into the humor column of Scientific American. So, they asked, there's the saran wrap. They did a great illustration here, and they asked some important questions like, what kind of elephant is it? Maybe a baby elephant. How do you get it on the pencil in the first place? Do you have to play baby elephant walk? So anyway, that was kind of fun. All right, but back to the science. So it turns out that, my colleague Tony Hines always brings up a nice quote from Einstein that says your model has to be just simple enough, but not too simple, right? So as simple as you can make it, but not too simple. It turns out this linear term here is way too simple, but even this next more complicated model is still too simple, right? It actually turns out that when you go to such high displacement, such high strains, you need to, if you're going to do a continuum model of graphene, you need a better model than this, right? And this was the kind of endeavor undertaken by a student in Jeff Kaiser's group with Chris Marianetti, a theorist as well, right? And what they did was really kind of go back to the drawing board and think about, how do you look at the stress strain behavior of this 2D material under very, very large strain, right? And so first you realize that this material isn't necessarily isotropic, and so all of these elastic constants are not scalars, but tensors. And now you do this beautiful tensor expansion. So there's your strain, and this is your stress. This is all your strain terms here. Your strain is now this eta. So this is all these indices are either x and y, 1 or 2. So this first term here, this is just your normal linear term, and it basically has in it your Young's modulus and your Poisson ratio. But then you get to higher and higher terms. So they took this out, instead of just the quadratic term, they added 2 more terms here. And you can see these tensors start to get a little nasty. This is a nice 10th rank tensor. That gets a little fun. So if you try to think about, how many different terms are in this expansion and trying to fit all of those terms, I think it's like around 1,300 total terms. You're probably not going to be able to fit 1,300 free parameters to any kind of experiment. If you did, we would usher you out the building, never to return again. But it turns out that the magic of group theory, it rides in to save the day to a great extent, right? All of the or I would say the vast majority of the terms in these 10th rank tensors, or 10, 8, 6, 4, are related. And it turns out that actually in this second order elastic constant, you only have 2 independent terms. Again, that's the Young's modulus and the Poisson ratio. The third order term only has 3 then 4, and then 5. So altogether, going out to this fourth order term, or this fifth order in energy, fourth order in displacement, you actually only have 14 elastic constants. Not so bad, better than 1,300. Still, how the heck do you get that from experiment? The answer is you don't. Well, we'd like to. But that, you really have to think about doing experiments in very controlled geometries up to very high strain. We don't yet have the capability to do that. We have a lot of ideas. But instead, we went the other direction. We said, let's start with density functional theory, and let's do these experiments on a computer. Right? So the nice thing here is that now we can just take isotropic graphene, do a single unit cell or a couple unit cells just to check, and we just strain the material and look at the energetics and take some derivatives and do stress strain in that way. All right, so that's the idea. So you do all of, each one of these dots here is a DFT experiment. And now what we do is we adjust these 14 elastic constants so we can fit all of these experiments well up to very high displacements. And the important thing we learned here is that if we ignored even this highest order term, if we only took, kind of our original experiment was, our original theory was here, if we took just one extra set of terms, it still wasn't enough to fully reproduce these curves. We had to go out to this fifth order in energy. Yeah. Everything is in plane. Everything is in plane. Yeah. Yeah. That is still that still needs to be done. In our experiments, the amount of bending is so tiny. So we're all treating that, and this is an important point, is that this is a membrane with, in these experiments, we're assuming 0 bending stiffness, so infinitely flexible, and the radius of curvature, even if we have a 20 nanometer tip, is so much larger than the thickness that we're in the membrane limit. That's not true for every experiment or every case, right? So that does have to be taken into account. But if you look at the energy, I think Boris has some numbers. I've used your papers for looking at the bending energy of a graphene sheet. And if you plug that energy in, how much energy does it take to just bend the graphene around the tip compared to the strain energy? It's tiny in these experiments. So the nice thing here is once you have these elastic constants, you can actually be an engineer again and go back to finite element simulation. So you can plug these elastic constants in to Abacus or any other finite element code, and you can actually do these simulations now with this much better model for the mechanics of graphene. And so what you can see is a few things. So now if we're plotting here stress, right, as a function of a position in the membrane as we indent in the center, and you can see at relatively moderate deflection, we get isotropic response. This is what you expect for linear mechanics of graphene. Right? The stiffness is independent of direction. As you start to go to higher deflection, you start to see other terms turn on, and those other terms are not isotropic. So the higher order terms see the crystal symmetry, and you can see that becoming more and more clear as you go on. The other interesting thing you see is that this is right before fracture. You actually notice something interesting. You notice that the stress has actually gone down, right? And what that is, I can point it out here, right? It's kind of the same thing here. So if you can actually take part of your material over the edge and go actually over the top of this stress strain curve. Right? And so the idea there is that locally you have some area of just a few nanometers at the point of the tip that is actually thermodynamically unstable. Right? If you were just pulling that, the stress strain curve is negative and it would be unstable. It would tear apart as you apply force. But you still have a ring of material that's on this side of the stress strain curve holding everything together, so the whole system as a whole is still stable. Right? And that's what we have here. So it's kind of, your unstable material is stabilized by this ring right here of material that's on the left side of that peak, right? So that's, you kind of get this small instability, and as soon as that grows and reaches the edge of the tip, that's your fracture point. Right? So a little bit, very small correction to our understanding of where fracture happens. Right? So the nice thing is now when we compare to experiments, we actually get a much better, and this is now, there's really no difference at low deflection, but at high deflection we actually see there's a significant difference between the models once we do this higher order corrections. The other thing that is, again, we can plot the stress as a function of position and really look at what's going on right under the tip. More importantly, if you look at the maximum stress as a function of load, right, what we see is in the kind of the original model that we put out, right, the maximum stress, it doesn't go linear, it kind of curves up, not as a perfect square root, but you can still see it kind of curving off like this and only really flattening off at very, very high loads. But because of these higher order terms, these stress strain curves, or this stress versus load curve, actually flattens out more earlier. And now when we plug in, say for the 38 nanometer tip, if we break at about 3,400 nanonewtons, we can see that that corresponds to a breaking strength of about 35 newtons per meter. So this is actually a little bit weaker than we thought before. So it's about 34 newtons per meter. This is about, this should be capitalized, about 100 gigapascals. So in the original paper we said 130. That is not correct. It's based on a model that the experiment is correct, but the interpretation is based on a model that was too simple. This more sophisticated model going out to higher order terms suggests that 100 gigapascals is a better value. Still, again, that's a heck of a lot stronger than anything else. So it's a pretty amazing material. Other 2D materials, there's still many, many to test. This is just work we've done. There's been some other work in the literature that I haven't had time to put slides together on, but I think still most of the 2D materials haven't been rigorously tested. But we have done this same approach for molybdenum for MOS2. So that paper is here. Again, you can get these 14 elastic constants. The symmetry is very, very similar. And once again, you can do these experiments, and again, you can look at the load versus indentation depth, and not only do you get a good fit to the load displacement curve, but actually you get a good agreement between theory and experiment for the maximum strength, the breaking load as well. So this is very nice. So this was understanding of these 2D materials in the ideal limit of no defects. They break at their intrinsic strength. You have to do modeling. If you want to do continuum modeling, you have to go to 5th order in energy, 4th order in displacement to really understand that well. But once you have that mechanics, everything falls out, and it's pretty nice. What happens if now we start adding defects to the mix, right? And so we did a couple experiments about that. And the first one was to look at CVD grown graphene, where you have grain boundaries, right? And so the question is, once you have grain boundaries, is it going to be as stiff or not? So I think I'll skip over this. Just to show some images, this is, again, grain maps with color mapping and a TEM of 2 of the types of samples we looked at. We called this small grain, roughly micron-sized grain, and large grain, where we have tens of microns of the grain. And we came into this kind of, this was again in maybe 2011 or so, 2010, 2011. There was a little bit of a disparity in the literature. There was some initial experimental work showing that CVD graphene was very, very weak, right? So, these loads, instead of being thousands of nanonewtons for breaking, were tens to hundreds of nanonewtons. and you saw lots of hysteresis in the force displacement curve. So something was very strange, something that certainly looked like CVD graphene wasn't very strong. On the other hand, there was some theory, this is one paper that from Ruoff and Shenoy, that predicted that grain boundaries should be very strong. So what's going on here, right? Maybe a factor of 2 weaker than the bulk material, right? Well, one thing we discovered is that how you prepared the sample was absolutely critical. So the standard etchant, so when you made CVD graphene on copper, the standard etchant was ferric chloride, a printed circuit board etch. And when we made samples with ferric chloride, they ended up looking like this. They looked pretty horrible, right? But when we used a different copper etchant, ammonium persulfate, we got much better results, right? So it seemed that the ferric chloride actually was attacking the grain boundaries in this graphene and weakening it, right? So that was a crucial thing. We also did some work to kind of eliminate or just kind of clean up the processing as much as we could. We did kind of a dry transfer process, which helped things as well. The last thing we did is we've actually shifted over from doing all of our work in an atomic force microscope to using a nanoindenter. This took some hacking of the nanoindenter system because these nanoindenters are kind of designed for pushing on solid surfaces, surface of a metal inducing, indentations in the surface of a metal. So they can go and they can map surfaces and find the surface, but they're used to kind of pressing pretty hard to do so. And we had to kind of train it to be a lot more gentle so it wouldn't just break all of our membranes as it was looking for them. But that can be done. And then we could make lots of membranes, map them, and do automated testing, and so really start to get some much better statistics. And what we found was that if we looked at, again, stiffness and fracture load of exfoliated material, we saw that if we used large grain CVD grown graphene so that there shouldn't be any grain boundaries inside the membrane, we saw virtually no difference in either the stiffness or the fracture load. So CVD doesn't seem to be worse from a mechanical point of view. On the other hand, when we looked at this small grain CVD, we saw the same stiffness. That's a good check because small defects shouldn't change the intrinsic stiffness of the material. But we saw a noticeable reduction in the fracture load, and as one would expect, right? But it was a lot less than was seen before. So we're still in the range here of thousands of nanonewtons rather than tens to hundreds, right? And we demonstrated this. You can put some little beads on here, and this graphene membrane supports it. And we also did nanoindentation testing on single grain boundaries. So we took grain boundaries, we mapped them in TEM, then took them to the SEM and found the same grain boundary and did nanoindentation tests on those. And again, we saw that the loading force was lower on the grain boundary, but not dramatically so, a factor of 30% or something like that. So the nice thing is, we could be a little bit more quantitative now. Instead of just talking about, well, the fracture load was 30% less, we can now do the simulation of the experiment and talk about the fracture strength. And so that's where this nonlinear model comes in. We do the nonlinear modeling, and because we can now take any tip we want, any geometry we want, we can generate a plot of stress in this underneath the tip as a function of load. And what we could see is that if we take either the pristine or large grain, if we look at the decrease in fracture load for small grain, we see that it only corresponds to about a 5% decrease in fracture strength. And in fact, even and I think I have a plot somewhere. I don't know where that went. All right, sorry, I somehow I have the, yeah, so this is the stress versus strain. I neglected to put in a plot of the single grain boundary, but it's basically showing the same thing. The nice thing about the single grain boundary is that you can actually, we're using a different tip, but you can, because you have the finite element modeling, you can eliminate all those effects and you can generate kind of intrinsic properties. And what we saw was that right on the grain boundary, the strength was only about 10% less than the intrinsic material. All right, so we're running a little short on time. So let me just kind of give some indication of what we've been working on for the last couple of years and trying to finally start writing up. What we really want to do is try to look systematically at large ensembles of CVD graphene, which have all kinds of different grain boundaries, and look at the statistics of fracture. Eventually, we want to say, if I have a square meter of graphene, maybe in a composite where we've layered them up and put in all this kind of stuff, where are we actually going to fracture? So we may have one weak grain boundary in the middle that causes fracture of the whole thing. We have to be able to understand the statistics of this fracture. And so we're trying to do this by kind of adding simple grain boundaries and comparing experiment and theory for large ensembles of membranes. This has been just a huge amount of kind of work on the simulation, which is not my domain. This is my colleague Jeff Kaiser's specialty. But the real challenge here in the finite element simulation is the mechanics of what happens at the grain boundary. And again, kind of mating the approaches of atomistic approach, which we can't do for a large-scale simulation, with a finite element scheme. And the idea is to build something called a cohesive zone model to look at these grain boundaries and to try to make kind of a substitute for the detailed mechanics with a model of what's going on right at that grain boundary so we can match the materials or match the properties at the grain boundaries. So second experimental study is something we've looked at to put point defects into graphene. Again, this is motivated by the same thing. In a real mechanical application of graphene, you're going to have large sheets that are going to have grain boundaries in the sheet, but you're probably going to have to cross-link the sheets as well. And when you cross-link the sheets, you're going to have to put in point defects to, for those cross-linking sites, right? So what do those point defects do to the strength? And so what we did was just start putting in defects by oxygen plasma. So here we have kind of a perfect graphene sheet by AFM. This is an extreme case. We use an extremely sharp AFM tip, and we can actually see we put holes in the sheet. But what we see in general is, as a function of plasma time, we actually see a crossover between what we call sp3 defects. That's where we have an oxygen bonded to the surface, and then after a while, we start to etch holes. Right? So with that there's a crossover to the vacancy regime. And we're actually able to see that. This is Mauricio Terrones did some nice TEM for us, and we could actually see that this is in the sp3 regime. We have oxygen add atoms, and then with longer etching, we actually start to make holes. So what we see with lots of experiments is the following. We see that the Young's modulus stays, again, there's a lot of scatter in the data, but it stays relatively constant as we add these oxygen add atoms. Again, that's as to be expected. Small point defects shouldn't change the overall stress strain behavior of the material that's dominated by the bulk of the material. But then once we start putting holes in the material, there's less stuff. Every time you have one of these holes, the material will be more flexible around that hole, and we see the Young's modulus start to go down. Right? On the other hand, if you look at the breaking load, it starts to decrease as soon as we add even these sp3 defects. Right? And again, that's because breaking strength is a function of the weakest point, not the bulk of the material. But again, using our, we decided, because the Young's modulus is constant here, that we can still use our nonlinear mechanics model, at least in this kind of sp3 regime. Out here, it's another ball game, and we still have, that still needs to be done more rigorously. But at least at this point, when we're just putting in these sp3 defects and not actually removing material very much, what we see is that this reduction in breaking load corresponds only to a reduction of about 14% in the breaking strength, or in the breaking strength. Right? So I think this tells us that we can put a lot of cross-links, a lot of point defects into graphene, as long as we're not making macroscopic holes, but holes the size of a few atoms. We can still maintain very high strength. So we're already over time, although I started late. But I'm going to save maybe a few minutes here as maybe a caution and a little bit of a rant. Can I do that? Am I allowed to? Yeah, crazy rant. I mean, if the president can do it, right? Anyway, all right. So this is, I think, just kind of, this is now the transition in the talk from scientifically well substantiated data and arguments to opinion. So what, the opinion expressed on these slides is mine and mine alone. But it's I'll say it's based more on intuition and a little bit of logic rather than something more substantial, and I hope, somebody in the audience will come out with more substantial arguments. So I just wanted to mention that there have been a few papers talking about mechanics of graphene and other 2D materials that have come up with some rather counterintuitive results, and this is one of them. So this is in Nature Physics just 3 years ago now, and the claim is that if you take one of these membranes and bombard it with argon, so introduce defects in a different way than we did, without not using oxygen but using argon, that you actually stiffen the material. Right? And then the experimental argument was that the stress-strain curve goes from pristine like this. When you make a defective, it's steeper, and if you do this linear plus cubic fit, you get, if you just pull out the Young's modulus from that, it goes up. And it goes up by a lot. So if you start here, it goes up and almost doubles, and then starts to come down again as you get more and more defects, right? I look at these experiments and it's one of those things that you just get a funny feeling, but you can't say why you don't think, think something's funny. But, I do notice a few things. One is that the pre-stress changes a little bit, and so that, when you're doing this fit, you always have to be careful if one term changes. The other thing is that this indentation distance is not tiny, but it's not quite as large as one would like, and this force is still a little bit lower. They're going nowhere near this kind of maximum breaking load. Right? So, but I can't point to one thing and say that is definitely wrong experimentally. If I look at the theory, and please, Boris and others, join in here, right? So the idea is that there's thermal fluctuations in graphene at room temperature. And the model was to say if we put in defects, those suppress the thermal fluctuations. And there are a couple really funny things I see with this theory. One is that they write the energy of this membrane, to ignore all the terms here, but there's no contribution of tension to this energy, which is fine, maybe in the unstressed case, but again, even here they're showing there's a linear term, so there is a built-in tension, which they seem to ignore in the theory altogether. And certainly at high strain, the tension is a dominant contribution to the energy. So, all of these fluctuations change the energy of the membrane, but I'm pretty sure that once you put any tension at all, the fluctuations disappear. The other thing is, I love this, that they say we consider the point defects have infinite mass, which was a very interesting, that's a way to kind of pin them down so that they don't move. So I don't know. It seems a little hokey to me. Can we eliminate this from the record? No. But this isn't the only such claim. This is a little older. This is from 2009. This was again a kind of a molecular dynamics simulation of bending of a nanoribbon. And the basic idea is that in your MD simulation you make a a 5 nanometer long little thing and you bend it with a 0.5 nanometer indenter, which I wish I had that, but you can do anything in MD, right? And you see some kind of cubic behavior and you say, hey, this is like a beam bending, right? And I can look up the formula. There we are again. Look up the formula for beam bending and it has Young's modulus in it, right? And so, and it goes like, so you see something varying as like the cube, inverse cube of the length. And you say, aha, see, it must be this formula. And they get 7 terapascals. Right?
This is my rice colleagues.
Yeah, I know. I know. It's nuts. This is nuts. Yeah. No. I made sure you weren't on the paper. So, Anyway, more recently, yeah. Here's another claim using Raman spectroscopy, where you take a membrane and you let it balloon in and out, and you look at the Raman shift, which is a very nice experiment, well done. The shift in the Raman modes as a function of pressure. The nice thing with hydrostatic pressure is that you know the shape of the membrane very well. It's a nice, very controlled experiment, but if you're using the Raman modes to calibrate the strain in the membrane, you have to know the shift in Raman modes with strain. That may not be as well understood as thought. In any case, again, now we get 2 terapascals. Right? So I wrote a comment to Nanoletters about this paper. Driven crazy, right? And I raised a few points. One is that, our nanoindentation tests had been repeated many times and, always gave the same thing at different campuses, et cetera. They're pretty rock solid, I would say. But the other thing is that, so this is more toward the first paper, of the 3. I don't understand this whole idea of fluctuation. If you suppress fluctuations, the Young's modulus goes up. I mean, I understand that. That's well known from, rubber bands, or, how fluctuations dominate the mechanical properties. But that would tell me that if you take bulk graphite with there's no fluctuations in bulk graphite because you're constrained by the lattice. If you separate it out into single flakes, I would expect the Young's modulus of those flakes to be lower than 1 terapascal. And then if we somehow clamp them with these infinite mass defects, we get back up to 1 terapascal. That's what I would expect. But instead, they start at 1 and go up to 2, right? Again, I don't understand how that can be, right? If these fluctuations are so dominant. Again, we're also getting numbers that, if you just think about graphene, in plane should be the same as graphite. The interlayer interactions are weak, right? That's why we can exfoliate this stuff. So you should get the same behavior for in-plane deformation of graphene and graphite. A couple other things. One is DFT is pretty darn good, especially, it always has problems with things like band gaps, but for structure and for basic energy, it is extremely good. And especially, if you look at our higher order modeling, it fits our data extremely well. It predicts breaking strengths, all kinds of stuff. If it were that wrong to predict a Young's modulus of 1 terapascal where it should be 2 or 7, right? Then, quantum mechanics would have some real problems and we would have noticed some other cracks in the foundations of all of solid state physics. The other thing is that Young's modulus is basically a spring constant, right? And if you have a spring constant at a mass, you have something called a frequency, right? And we measure those frequencies with Raman spectroscopy. And if you had these variations in Young's modulus by factors of 2 or more, you'd expect to see Raman frequencies going all over the place. And they don't. They stay in the same place for monolayers, multilayers. So the whole thing makes me very skeptical. I can't, point out exactly what's wrong in every experiment, only to say that, I brought up there's the kind of Carl Sagan quote of, extraordinary results require extraordinary evidence or something. That's a terribly mangled quote, but that's, if you see something that shouldn't make sense, you better really have it nailed down experimentally. I wrote this to the nano letters for that, the Raman experiment, and they wrote back, they said, well, we don't publish retractions because we don't want the journal to become a forum of the validity of results, which I thought was rather shocking. But anyway, I hope we here as students can aspire to something a little bit more rigorous than that. But anyway, I still send stuff to nano letters. So I think I'll end here and take any questions or discussion over lunch. Maybe I'll leave on here that there's a lot of good stuff to do. Once you have, I'm going to just highlight where we are. Once you can put on very high strains and materials, you can do all kinds of crazy stuff. So I think Evan will be talking about that later.
All right, so maybe we can have time for one question.
So you mentioned you're characterizing the oxygen-edged graphene membranes using TEM, right?
Yeah.
What kind of energies are you using TEM?
I think they were, yeah, I know. So were we destroying the graphene, right? So in graphene, it's a much worse problem with TMDs. In graphene, I think it's pretty well established that if you're using 80 kV, you can minimize the damage, right? I'm gonna, if Mauricio were here, I would let him answer the question, but all I can say is it's an extremely experienced graphene TEM group that did this, and they know about that problem. So I'm pretty sure that they didn't put the holes in themselves. And we saw a variation with different types of samples that we had destroyed intentionally. So, nothing was out of the ordinary there. Yeah.
Is there a reason? I mean, the other groups seem to have quickly switched to the other
Yeah.
materials. Does graphene hold as something special mechanically that?
Well, I think graphene is still the strongest material, and so for pure mechanical applications, I think graphene is where you want to be. I think, again, Evan will talk about other strain-induced changes and all kinds of interesting things. We did some work on piezoelectricity. So we've done some, but it's whatever grant you get to do whatever science you can do, right? So, that's the real reason.
With this next speaker is Professor Ashby from Stanford University. He's going to talk about 2D materials, piezoelectrics.
Okay, should we try? Yeah, that'd be great. Oh, does this have a laser pointer on it?
It doesn't work.
Is this a laser pointer?
Yeah.
Awesome.